So here we are on the final question of this June 2014 paper, and we're looking at some springs. So let's have a look. A light spring of unextended length of 2 centimeters is hung from a fixed point. An object of weight 3 Newton is hung from the other end of the spring here, and shows the length of the spring when the object is in equilibrium. So this is the important point. And then we've got this over here where it's being pulled down to this new position. But this diagram we're not going to worry about just for the moment. It's just this first one to begin with. So the first part of this, A, show that the force constant of the spring is 50 newtons per meter. Okay, well, let's have a go at that. Let's just get my pen ready. So we should know that the force is directly proportional to the extension, and that constant of proportionality is the force constant. So if I rearrange that, my force constant is going to be my force divided by the extension. And if we go back to the blurb in the first part, it tells us that the original length is 2 centimeters, and when the object is in equilibrium, it's 8 centimeters. So that tells me that my extension is 8 minus 2, which gives me 6 centimeters. If we notice, the unit it's asking us to get it into is in newtons per meter, so we'll just change that into meters. So that's the same as 0.06 meters, and the weight is 3 newtons, so 3 divided by 0.06 is indeed equal to 50 newtons per meter. Okay, this is the first time we've had one of these show that something type questions in this paper, and they do them because obviously they want to see if you can work it out, but what they are knowing is that you're going to need to use this in the later parts of the question. So let's just have a look at what that is. The object is pulled vertically downwards. Figure 2 shows the new length of the spring, and it's now here at 12 centimeters. And we've got to calculate the change in elastic potential energy, delta E, in the spring. So what we're going to have to do here is we need to know how much elastic potential energy have we got over here, how much elastic potential energy have we got over here, and subtract this one from this one, and we've got our answer. Okay, so elastic potential energy is, let's just call that E, is going to equal, oh, my mind's gone blank. What is it going to equal? Half kx squared? That sounds familiar. Okay, so if let's do our object over here, so that's going to give me a half times 50. And remember, our extension was 6 squared, and over here that's going to be a half times 50 times 10 squared. Quite a common thing to do is people just find what's the difference in the extensions and they square that. That won't work. You've got to work out the potential energy at this point and the potential energy at this point. If you were to go, well, this one's extended by 4 centimeters more, therefore if I go a half times 50 times 4 squared, that will not give you the correct answer, because, well, you can work it out as when you find this and you find this, it doesn't give you the same answer as when we do it as 4 squared. Okay, let's get on with this then. So this one over here will equal 0.09 joules. Oh, get to a pen. and this one over here equals 0.25 joules. So therefore delta E is going to equal 0.25 take away 0.09, and that comes out as being 0.16 joules. And there we go. That's not quite the paper finished. I thought it was. Let's get on to part C. Okay, I said it was part C, it's not, it's part B, part 2. Okay, so let's have a look at this. We've got the object is released from its position shown in 7.2, so that's where we've been stretched down to 12 centimetres. And calculate the initial upwards acceleration A of the object. Okay, so when this is let go, obviously what we've got going on here is we've got this 3 newtons, and then this 3 newtons is being held by whoever's pulling the thing down with some extra force. As soon as you let them go, we've still got this 3 newtons acting down, but now we've got a force acting up here, and I'm going to call it the tension. And what we know is that that tension minus the 3 newtons, that's going to equal our force, and then because we're after the acceleration, we know that the force is equal to the mass multiplied by the acceleration. And of course we don't actually know what the mass is, but we are told that the weight of the object is 3 newtons. So the mass, well, let's go, the weight of the object is the mass multiplied by G. So the mass is going to equal the weight divided by G. So that's going to equal, so that's 3 divided by 9.81. So there's the mass of our object. Now let's find what the tension is. Well, the tension T is equal to the force constant multiplied by its extension. So our tension is equal to 50 newtons per metre, and it's been extended by 0.1 of a metre. There's the 10 centimetres. So don't forget that it was 2 centimetres in original length. So that gives me a tension of 5 newtons. So my resultant force, if we come back over here, let's bring that down to try and make it sort of go a little bit logically. Therefore is going to be, so my resultant force is 5 minus 3, so that gives me 2 newtons. And now let's use my F equals ma. So because F equals ma, I know that, and I'm after the acceleration, so that's my resultant force F divided through by my mass. So if I put that in, that gives me my resultant force divided through by my mass is the same as multiplying by 9.81 and dividing by 3, and that should come out as being 6.5 meters per second squared. And that's the paper done.